So I'd like to introduce our speaker for today, Professor Brian Korgel. He's the T. Brockett Hudson Professor of Chemical Engineering at the University of Texas at Austin. And his research area is nanomaterials, chemistry and complex fluids. He's got his PhD from UCLA and took up a postdoctoral fellowship at University College Dublin, and then joined the University of Texas at Austin. So he's been a visiting professor in Spain, in France and in Beijing. He's currently, and I guess this is our main interest, and the reason he's here in our school is that he directs the Industry University Cooperative Research Centre for Next Generation Photovoltaics. And he's co-founded two companies, interested in Innovolite and Pinion Technologies. So Innovolite, many of us here know very well, and perhaps Pinion Technologies, what you'll tell us about today. So he served as an associate editor on chemistry of materials. He's published more than 200 papers and received various honours, including the Professional Progress Award from the American Institute of Chemical Engineers, the Roy Saunier Medal from the ISHA, and is a fellow of the American Association for Advancement of Science. So please welcome Brian to speak to us today.
Great. So thanks very much for the introduction, and it's a pleasure to be here. So my group does nanomaterials chemistry, so that's essentially the platform that we work from, and I'm going to talk about some of the work we've been doing really, I guess, over the past 8 years or so on photovoltaics. So the general concept's pretty simple. Essentially make an ink that we can spray or deposit onto a substrate to make solar cells, and maybe solar farms or portable power. Okay, so I'll talk about where we are in that and some of the chemistry. So when I'm thinking about photovoltaics, as an academic, I like to think about disruptive solar. So what can we do to change the way solar cells are made or how they're deployed? So certainly highest on the list is grid parity, solar power with grid parity. So where you have the cost of solar energy is equal to or less than the cost of fossil fuels. So in order to do that, you need a technology that's relatively inexpensive to manufacture, but then in terms of solar cells has high enough efficiencies so you have low balance of systems cost and can get down dollar per watt kind of sunshot goals. So that's one thing. There are a couple of other goals that we're thinking about. We're not the only ones, but I'm thinking about portable power. Okay, so how can you create energy harvesting devices that can be deployed in cities and urban environments, on automobiles, on airplanes, and that sort of thing. And in a lot of these applications, the efficiency is important, but it's not necessarily the primary concern. You're thinking about weight, form factor, simply how those things can be integrated into the environment. The third thing that we've been thinking about a lot is multi-purpose solar, or what I'd like to call multi-purpose solar. And that's where you have a solar cell, but it has another function as well. So maybe a fabric, okay? So like a shirt that works as a solar cell, and its primary purpose is a shirt that you wear, but it harvests energy to power electronics. Maybe solar materials that serve as camouflage in some capacity, or architecture and design. So these things of portable power, multi-purpose solar. Sure, efficiency is important, but I would say form factor, types of materials that we can use are more important. Okay, so what we're really thinking about, what the philosophy I guess I have in my group is thinking about changing the way solar panels are made. So can you print solar panels like you do newspaper? Can you make paints that you paint on the wall that can work as a photovoltaic? Okay, can you make solar cells that are plastic, lightweight, and flexible? So every solar cell has a pretty simple structure. So it's usually a sandwich device. So you have a main light-absorbing layer, that's your semiconductor that absorbs the light, creates electrons and holes, and then you have a built-in junction, so some sort of heterojunction or PN junction. I'm going to talk mostly about CIGS, so copper, indium, gallium, selenide. CIGS is p-type, and you have to put an n-type layer on the top of that material. And then you have the semiconductor sandwiched between two electrodes. So you have a top electrode layer, bottom electrode layer, and then some mechanical support. And those layers need to be electrically conductive, but they also need to let light through, at least one side. Okay, so that's the structure. And what we want to do is come up with a way of essentially printing that device, try to avoid as much as possible vacuum processing and high temperature. At least that's the goal. So a lot of the work that I'll talk about was partly inspired by this particular paper that came out from Paul Alvasatos's group in 2005 in Science. There's even work before that. So I did my PhD at UCLA. I finished in 1997. At that time, I was looking for postdocs. I was doing nanocrystal research. And one of the areas of interest that was emerging a little bit was in photovoltaics. So Paul Alvasatos's group, for example, had an early paper taking cadmium selenide nanocrystals and embedding them in organic semiconductors to make a solar cell. And I think that paper came out in 1996. At the time, there was some interest in using nanocrystals for photovoltaics, but in the United States in 1997, there was almost zero funding, I would say, for photovoltaics research. So that was one of the reasons that I went to Europe for my postdoc. I ended up doing something not related to photovoltaics for my postdoc. I was looking at nanoparticle self-assembly. But there was a lot of work on dye-sensitized solar cells. I was part of a European project with Michael Gretzel, for example, and there was work being done in Europe. And so the work being done on nanocrystals, the idea was somehow to use the unique size-dependent properties of quantum dots to make better solar cells. That was kind of the philosophy people had had. And then this paper came out in 2005. And I think it showed a different way of using nanomaterials. Okay, so the idea wasn't so much use the unique properties of quantum dots to make better solar cells, but maybe use the nanocrystals as a new strategy for actually processing materials, which made a lot of sense to me because essentially you could take a material that works well, that you understand in terms of vapor deposition, and all you're trying to do is find a different route to making that particular structure. So what they did here in this paper was make devices with cadmium selenide and cadmium telluride, and they would use the nanocrystals or nanorods as layers that they could then sinter at lower temperature. And they were making devices with about 3% efficiency. And so this was very interesting to me. And so I was involved in Innovolite. So Innovolite was founded out of my research lab in 2001. And around this time, Innovolite had started working on solar cells. And one of the things they were thinking about was using silicon nanocrystals as an absorber layer in photovoltaics. And so this work was coming out of Berkeley with cadmium telluride. The work I was intimately familiar with in Innovolite using silicon, and each of those had problems. Okay, so at the time, cadmium telluride had a real problem with stability. People eventually figured that out, sprinkle a little bit of copper at the back contact, and First Solar now works, but people didn't know that back in 2005. Silicon has some issues with absorption. It's an indirect bandgap semiconductor, so it's a pretty weak light absorber, even the quantum dots. So if you look at what could you potentially use as a material, as an ink that hadn't already been made and also makes some sense in terms of device performance and that sort of thing. There aren't a lot of options. Okay, in terms of thin film materials that are commercial, direct bandgap, there's amorphous silicon, cadmium telluride, and there's CIGS, so copper, indium, gallium, selenide. So the idea that we had in 2005 was try to make copper, indium, gallium, selenide inks. And at this time, nobody knew how to make nanocrystals of this material. And so CIGS is an interesting material. Its record efficiency with co-evaporated devices is over 20%, power conversion efficiency. The material itself is isostructural with a zinc blend, but it's tetragonal. So the unit cell is tetragonal because you have compositional ordering of the copper and the indium in the material. And the way that the high efficiency devices are usually made are either ultra-high vacuum or selenization, where you're selenizing layers of copper, indium, and gallium at 500 degrees C. So the idea was, can you make nanocrystals of this material and print them into layers? So that's kind of where we started. And the typical CIGS device is soda lime glass with molybdenum back contact, CIGS, cadmium sulfide buffer layer, and then the N-type layer is zinc oxide. And then on the top, some sort of TCO layer. Okay, like ITO. And so can you make these nanocrystals? So back in 2006, it wasn't obvious that you could make nanocrystals of copper, indium, gallium, selenide. Okay, this is a quaternary material with 4 elements. And usually if you combine 4 elements into a flask and heat them up, you get a wide range of phases and compositions. And so we set out to do this, and it wasn't clear that you could actually make this material. There were a couple of reports in literature for making copper indium sulfide, for example. Most of these relied on single source reactants. So you had a reactant with copper and indium and 2 sulfur atoms, and the idea was to take this single source reactant and decompose it into nanocrystals. And there was a prevailing thought that the only way you could control stoichiometry of nanocrystals of ternary compounds like this is to start with this fairly complicated single source reactant. And so that actually turns out not to be true at all. Okay, so chalcopyrite phase, copper indium sulfide, copper indium selenide, and CIGS turns out to be a really stable phase. And so, we tried some of these methods in the literature. None of them worked at all, really. And so we went back to some chemistry that we knew how to do in my group for making copper sulfide. So these are copper sulfide discs. We could make them pretty monodispersed. You just take copper reactant, sulfur, put it in dichlorobenzene with a bit of oleolamine and octanoic acid, heat that up, and you get fairly monodispersed particles. And so what my student did, Matt Panthani, is just added some indium. And it actually took us a year just to try what we knew how to do in our lab already. I think reading papers, we were psyched out by the literature and thought this was going to be really hard. It turns out it's not that hard. And so you can make very monodispersed copper indium sulfide. Very straightforward way. This is a chalcopyrite phase, and so if you look at the X-ray diffraction, there's a small peak here, the 211 peak, and that's indicative of the cation ordering in the material. Okay, so then we extended that to copper indium selenide. We had to change solvents a little bit because selenium's is not soluble in the solvent we're using for the copper indium sulfide. And oleolamine turns out to be a really good solvent and capping ligand for copper indium selenide. And so this reaction turns out to be really, really easy. Essentially, you can just combine copper salts, indium salts, and selenium at room temperature with some oleolamine and just heat it up in the flask and let it sit there at 240 C for an hour, and you get chalcopyrite phase copper indium selenide. So this reaction, this chemistry that before we had started doing it seemed really complicated, turns out not to be. So this phase is a very, very stable. You can play games with the actual reaction, but you have to be careful. So a lot of colloidal syntheses use phosphines, and those phosphines can tie up the copper and the indium and essentially poison your reaction. But they cannot. But a reactant like tributylphosphine can be a very effective delivery vehicle for selenide, as long as you don't have too much of it. Okay, so there are some things about the synthesis where the shapes can vary depending on reactants and that sort of thing, but overall it's a very straightforward reaction. So then if you add gallium, you can actually tune the indium to gallium stoichiometry systematically just by how much gallium you add into the reaction. Okay, so that works. You can make copper zinc tin sulfide by similar chemistry as well. So this class of compounds has turned out to be really quite straightforward to make. So that's one reason I think that there's so much interest around the world in these type of inks for photovoltaics, because the synthesis, the chemistry turns out to be pretty straightforward. This is one of the undergrads who did a lot of work in my group early on, Daria Reed. So all of this is done on a Schlenk line. You're going in and out of a glove box. Okay, so you can make the inks. That's not really a problem. So how about the devices? So you have this ink. You have a stepwise synthetic process. You're not painting the entire solar cell structure, obviously. We're focusing on painting the absorber layer itself. When we first started out, the question was, what's the best way to deposit the ink itself? So we did a lot of drop casting. So this is an array of layers where we were trying to understand how to avoid cracking in the deposition, etc. And it took us a couple years really to figure out how to make some devices that worked. And so using a standard structure of soda-lime glass, molybdenum, copper indium selenide nanocrystals with a cadmium sulfide buffer layer and zinc oxide. This is one of our devices from 2007 or 2008 with a power conversion efficiency of 0.34%. So for a while, we were really stuck at this 0.5% efficiency. And what we realized is that we're not limited to using molybdenum, for example, as a back contact. So the work function of molybdenum is not very well suited actually for CIGS, but it's used as a back contact for CIGS because it's thermally stable, and you get a selenization layer between the copper indium gallium selenide and the molybdenum that then works to sort of take care of that work function mismatch. And so we're not, in this case, not doing selenization at all. So you end up with molybdenum metal interface with copper indium selenide, and you end up with a Schottky junction. So that's one of the problems with this device structure. So we started looking at other metals, so higher work function metals like gold, for example. And just by changing around some of the device layers and that sort of thing, we were able to go from about 0.3 or 0.4% PCE to 3%. Okay, so this is our roadmap of efficiency up to 2010, showing kind of where we started. I think our first device efficiency was 0.0001%, which was like two layers kind of alligator clipped together, and we're like, a photovoltaic effect, you know. And but you know, it seems crazy now, but at the time, this was an ink that was just smushed onto a substrate at room temperature without any sort of heating. And the question was, could you take this CIGS material with these C18 hydrocarbon ligands and actually extract charge from it? It wasn't obvious that you could do that, and I still don't think it's really obvious you can get to 3% efficiency just by doing that, but that's essentially what you can do. So we started changing things around in terms of deposition. My students went to the toy store and bought an airbrush and made life simpler. We could make these things on plastic. So 2 to 3% on plastic, and that's kind of where we are. So one of my students is working on very thin nickel-coated PET for some applications, and so this is just a device with 0.35%. But the interesting thing is you can bend it around, and it still works. Okay, so you can do chemistry on CZTS as printed devices. This was from 2009, but again, kind of 1% efficiency. So the question is how do you make these things better? So we started playing around with ideas like nanowires. So you can make nanowires of copper indium selenide. So Jennifer Hollingsworth at Los Alamos was the first to demonstrate this with the JACS paper. You can use bismuth seeds, and then you do the colloidal growth, and nanowires grow from the bismuth seeds with a solid solution liquid solid growth. And these are crystalline nanowires. And so you can make these things, and you can make photovoltaic devices out of them. So this was one of our first devices, 0.014% efficiency, but they worked, 0.1%. And so we've still been doing things with nanowires in terms of making fabrics, self-supporting fabrics that can be photovoltaics, but again, not particularly efficient. All right, so that's, I don't think a solution to the problem. So how do you get to the 10 to 20% efficiency? And the challenge is really the electron transport. So the devices that are have 3% power conversion efficiency are actually very, very thin. So if we just spray a layer of nanocrystals as we would into a device onto a substrate and look at it, you see that most of the light's actually going through the material. So the film is very thin. It's not absorbing that much of the light. It's absorbing 10% of the light or so. And so if you measure the internal quantum efficiencies of these device layers, that very thin layer, the internal quantum efficiency is around 40% across a range of wavelengths. If you increase the thickness, so you're absorbing more light, the IQE ends up dropping pretty significantly down to 20% or so. So this really illustrates the challenge with these inks. Okay, the inks themselves, the nanocrystals, are coated with these hydrocarbon, and that hydrocarbon is important for the synthesis, controlling the synthesis, the dispersibility, the processability, but then it's inhibiting the performance. Okay, so when you create your electrons and holes, they're just not extracted very well. If we could get internal quantum efficiency of 40% in layers thick enough to absorb all the light, we'd have 10% PCE. We just don't know how to do that yet. So how do we get there? One way is maybe annealing, pop the ligands off. It turns out if you just under vacuum anneal these nanocrystal films so the ligands pop off, then the device layers don't work at all. Like there's 0% PCE. So those ligands are somehow passivating interfacial traps and allowing the devices to work. So you can't just get rid of the ligands. The devices don't work that way. So you have to do something perhaps to get rid of oleolamine, but put other ligands on there. So in the lead sulfide case, like Ted Sargent, Bawendi recently had a couple of papers in Nature showing that they have really good control over how to do that with lead sulfide now. But on copernadium selenide and CIGS type particles, nobody really understands that surface chemistry yet, and we don't either. Okay, so can you use shorter ligands? One approach that people have used is selenization. Okay, so I'll show a bit of data from our group. We can get to about 8% PCE if we selenize and sinter our CIGS films. Hugh Hillhouse's group and Rakesh Agarwal have gotten above 12%, and I think that they've gotten even to 14%. I know at least one company is up to 14%. So one way of getting higher efficiency from inks is to sinter it. Okay, resort to high temperature, annealing under selenization, and that kind of works to some extent. There are issues in cost and scalability, but you can definitely do the sintering of the layers. This is a 7% efficiency device from our group. So can you do that same sintering, but not by going to high temperature under selenium? So this is a tool called the Pulse Forge tool from a startup company in Austin called Novocentrics that we've been working with for a few years. And this is a really interesting tool. It's a broadband white light source. It's a xenon lamp, so it's a flash lamp. And it's very high power, and you can take your films up to even close to 1,000 degrees C in less than a millisecond, so 500 microseconds. This is a tool that's been designed for manufacturing. So one of the things that Novocentrics does is they make RFID tags. So they'll make copper inks. Sort of print those on paper and then run that through this pulse forge technique to sinter the copper together. So this is a tool that's designed for high throughput manufacturing. Okay, so because the light sources pulse very rapidly, you have rapid heating but then rapid cooling between the pulses. So this tool is designed to get very high temperatures, but spatially localized, say on the top of substrates. So the idea is maybe to have copper indium selenide inks on plastic. Okay, you can't take the plastic and put it into a furnace of 550C, but you can run it under the pulse forge tool and get the copper indium selenide film to 500C without destroying the underlying layer. So we've been doing a lot of work with this tool. We take copper indium selenide nanocrystals. So it's really easy to just blast layers off of the substrate. So you actually it takes some fine tuning to figure out, first of all, how not to destroy your films. But then in a window of conditions, you can sinter nanocrystals. So you can sinter them without the presence of selenium with this rapid pulsing. So on this panel F down here on the bottom is a sintered layer of copper indium selenide. And if you look at the X-ray diffraction, it's clearly sintered. And you can do things. In some cases, we find that we get Wurtzite phase. So this is really a kinetically limited grain growth that's happening under this process. So you can make these films. So far, we can sinter layers, we can sinter the nanocrystals, but we can't make even decent devices from this. So we don't know yet what's happening in that sintering process, if we're creating a lot of traps of some sort. But if you look at an as-printed device that's typical 1.2% power conversion efficiency, and you sinter the film, you basically lose the device performance. But what I want to talk about briefly is this intermediate region where if we use the pulse forge and do photonic curing, where we're not sintering the nanocrystals, but we're kicking ligands off and we're getting particles to we're densifying the films, okay? And if we do that, so if we look at the device performance here in the middle, the power conversion efficiency of that device is 1.25%. So we essentially densify the film. The PCE is not improving, okay? But the short circuit currents are much higher. So we're extracting a lot more charge, but we're losing our VOC, okay? So that's one thing. So when we looked at we did IPCE measurements on the device. And so doing IPCE under a white light bias, for example, if we make a device as deposited without the photonic curing, which is shown up in the inset, there's no difference in the IPCE or the device response under white light bias or not. But when we do the photonic curing process, we found this dramatic increase in IPCE at lower wavelength under white light bias. So that was one thing that was kind of interesting. The more interesting thing was under white light bias. So once you go under kind of sunlight illumination conditions, the external quantum efficiency, the peak external quantum efficiency of the device was over 100%. So when I first saw this data, I thought we were doing something wrong for sure, as everyone should think that. All of you, we have a paper on this. If you haven't seen the paper, I'm sure you're like, oh, that's wrong. You're not doing your device measurement right. And that was what we thought at first. So my student Jackson made a few other devices this way, the same response. So then we're like, okay, what's happening there? Went to one of my colleagues in electrical engineering, Sanjay Banerjee's lab, where they have IPCE testing, and did IPCE on their instrument, got the same response, okay? So we started thinking, what's happening here? So one explanation for having external quantum efficiency over 100% is what if we're creating multiple excitons in this film, in the nanocrystal film, and we're actually able to extract more than one exciton per absorbed photon. And there is some precedent for this happening in nanocrystal films. So there was a paper out of NREL from Matt Beard and Art Nozick in Science on lead selenide nanocrystals, where they had peak EQEs of greater than 100%. So there was some precedent for it, okay? So clearly, I mean, we were getting this over and over again. And so we wanted to know, do we actually have multiple excitons in our film? So my students, Jackson and Doug, went up to Argonne National Labs to work with Rich Schaller and did transient absorption spectroscopy measurements on film. So essentially, we were looking at least in an optical signature for carrier multiplication in the film. So if we look at the nanocrystal film before and after photonic curing, the absorption edge shifts slightly to lower energy. Okay, and if you do transient absorption spectroscopy, so what you're doing is you're pulsing your film with light of one particular wavelength. So this is probably 800 nanometers. And then you're measuring the absorbance spectra. Okay, so in transient absorption spectroscopy, you have a pulse of light. Okay, so you're photoexciting your nanocrystal at a particular wavelength, and then you're measuring the absorbance spectra. And so what happens is you see a bleach in the absorbance at the band edge. Okay, so when you photoexcite, then you get a reduced absorbance at that wavelength. And so where you see the peak, that corresponds approximately to the optical gap. And so the way these measurements work is if you're looking for carrier multiplication, what you'll do is you'll do this transient absorption spectroscopy measurement with a pump wavelength that's relatively long. Okay, so 800 nanometers. There's not enough energy in that one photon to create more than one exciton, unless a nanocrystal absorbs more than one photon at one time. So under low fluence, the nanocrystal absorbs the photon, you create an exciton, and you see a bleach corresponding to that single exciton. So you can create more than one exciton in the nanocrystal if you increase the fluence enough so the nanocrystal absorbs one photon, you have one exciton, then before that exciton can relax, it's hit by another photon. So you can create multiple excitons with the long wavelength light by multi-photon absorption. If you are pumping with 400 nanometers light, so in this case 3.1 times the band gap, okay, times the optical gap, there's 3 times the energy needed to create an exciton, then that one photon has enough energy to create more than one exciton, okay, possibly. So the way these measurements work is you take the 800 nanometer light at low fluence and you measure the lifetime, okay, the decay in the signal or the relaxation of the excited state. And then you do that at low fluence, so that's a single exciton relaxation rate. Then you go to higher fluence, so you're pumping where you get multi-photon absorption. You're actually creating multiple excitons within the nanocrystals. And then you measure the rate of decay, and that rate of decay is faster, okay? And so by doing that, you get a baseline of single exciton decay, and you get also an estimate of multi-exciton decay rate. So then to determine if you have carrier multiplication in your nanocrystals or in your film, you do the pumping at with the higher energy photon at low fluence, so you don't have multi-photon absorption, and you look at the decay rate, okay, of that excited state and compare it to the low fluence data. And so what we found is we have carrier multiplication in our films. So when we're hitting the nanocrystals with 3 times the optical gap, we create multiple excitons. So in these films, we do have multiple excitons being formed. So we've done some more measurements looking at nanocrystals of different size. So we wanted to know what is the threshold energy, photon energy for multi-exciton creation, and what's the quantum yield. So these are measurements for 3 different sizes of copper indium selenide nanocrystals. You do the measurements, the peak in the transient absorption spectra is size dependent, so it shifts to shorter wavelength with smaller quantum dot size. And you can get things like the carrier cooling rate. Okay, so initially when you create your your excited state, you have a hot electron, you can actually measure the rate of cooling of that hot electron to the bottom of the conduction band or the top of the valence band, and look at the size dependence of that, and it essentially goes as predicted, or similar to other types of quantum dots. And then looking at the transient absorption spectra for these 3 different sizes, we can back out the MEG threshold, or the threshold for carrier multiplication. So the threshold for carrier multiplication in copper indium selenide is about 2.4 times the optical gap. Okay, so you have to have 2.4 times the optical gap to get multi-exciton generation. And then the MEG efficiency in copper indium selenide is 36%. Okay, so there's some error in that measurement, but about 36%. So that means that if I am at photoexcitation of 3.4 times the optical gap, I'm generating 1.36 excitons. Okay, so all of that's pretty consistent with what we're seeing with our EQE measurements. The thing that's, throws people off, including us, I would say, in the EQE, is the fact that you have such a low EQE at long wavelength, and then suddenly it spikes up. Okay, and what we think the reason for that is that these films, because we're desorbing a lot of the ligands, are actually pretty trappy. Okay, so when you're shining the white light bias onto the films, you're filling some of these traps, and that's why you start to see the ability to get the multiple excitons out. But the overall device response, the power conversion efficiency, is still relatively low. Okay, so how do you make that better? All right, how do you extract multiple excitons and make better devices? So this is the Nozick-Beard paper, and our idea is to do the photonic curing. Okay, so we get high short circuit currents, and yeah, multiple exciton extraction is interesting, but really what we want is high short circuit current, but a high VOC. So how do we get our VOC back? And the idea and what we're looking at now is then trying to do the photonic curing process and then repassivate the surfaces in some way. So, I don't know if that's, hydrogen passivation or something, but some way of passivating these surface traps. And I don't know if this approach will work or not, but that's essentially what we're working towards. Okay, so so when I give this talk, it's always kind of a letdown to me in a way, because we haven't solved the problem. We don't make 15% printed devices. If I did, I would be probably really wealthy right now. But I would love to be able to do that. It's a really hard challenge. I would say in terms of using nanocrystals as photovoltaics, seeing where the field has come, just even in the last 4 years or so, it's pretty remarkable. Going from where the record efficiency was, 2.5%, now as printed devices are above 8%, and with lead sulfide, people understand how to tune the electron affinities of lead sulfide nanocrystals by changing capping ligands and playing games with those. You can certainly sinter nanocrystal devices and get 14-15% by doing that. People have done this with cad telluride. They've done it with CIGS, for example. We're starting to see new photophysics that people thought was probably impossible. I mean, at one point, people were hotly debating whether you even had more efficient carrier multiplication in quantum dots compared to bulk semiconductors, and now that's a resolved issue. You definitely do. The question is can you extract those multiple excitons? And it looks like perhaps you can. So the question is now, can you be printing using these materials and get to that 15 and maybe 20% efficiency? I think the perovskite work is on the one hand discouraging because suddenly people are making very high efficiency devices, but on the other hand very encouraging because there perhaps are solutions to these problems. Okay. So these are some of the students I wanted to acknowledge. So my first gen PV students, so Vahid, Brian, and Matt, who basically developed a synthesis from nothing when actually it looked, it was really unknown whether you could actually make this material, and now people around the world, really use their chemistry. So that's kind of interesting and exciting for the group. A couple of undergrads played a really key role early on. So Danny Helbush, who now is a PhD student with Paul Alvasatos, and Daria Reed, who's a PhD student at Texas A&M. And my next gen PV students, so Jackson Stoley and Taylor Harvey. Taylor's been doing a lot of selenization work, and Jackson's been doing a lot of surface modification and really discovered this EQE greater than 100% phenomena as well, and has been doing all the transient absorption spectroscopy. So be happy to answer any questions that you have. Thanks.
Thank you, Brian. A whole lot of really interesting stuff there, and a lot of overlaps with things we do here as well. So questions, please.
Yeah.
One thing about light, it's very interesting to get a 3% without any high temperature needing for the CIGS cell. One question is because you don't have the high temperature, so you won't expect the sodium diffusion from your your glass from to the absorber. So in which stage you introduce the sodium into the film, or you don't have sodium?
In those, we don't have sodium at all. So in the selenization process, sodium is really critical. So to get up to 7 or 8% efficiency, I mean, in the selenization process, sodium of CIGS, sodium is really crucial for that, for the sintering. In our case, these as printed devices are not sintered at all. Where we're looking at the possible role of sodium, where it could be really important, is in the photonic curing. So there, we're dosing films with sodium to see if that influences the sintering under the photonic curing process at all. And that's kind of unexplored territory, just because you're really in this kinetically limited regime, and you don't have long-range diffusion of elements the way you do in selenization. But there we're really looking at sodium and the role of it.
Nanosolar had a trial printing CIGS,
Uh-huh.
and I think they got over 10%.
Right.
Yeah. So do you know what
They were doing selenization of their.
So and it was never cost effective, and I think they now.
Right.
So what's the critical step? What's the critical problem there? I mean.
Avoid selenization.
So it's just too costly.
Yeah, so not only do you have to heat to 550 C, you have to do it with the selenium vapor. And so one of my students just spent 2 months in Singapore, where they have a 2-zone furnace for selenization, and so they can control the temperature quite a bit more closely than we can at our facility in Texas, and including they have pretty close control over vapor pressure of selenium. And just small changes in selenium vapor pressure give pretty dramatic changes in terms of selenization and morphology. And you can do, people are pretty clever, and you can control that to a pretty good extent on manufacturing lines, but it's still, in the end, that control and the yield of devices is what's really limiting CIGS from becoming commercially viable in the way that cad telluride is. So cad telluride has kind of taken off, and First Solar can make really inexpensive devices. And if you compare the two processes of CIGS and cad telluride, you're subliming cad telluride onto a substrate at 400 C, and it's under vacuum, but it's not ultra high vacuum, and that's a pretty easy process to control compared to the selenization. So I would love to figure out a way to get rid of selenization and sintering. But the problem is as you can see, if we get rid of it, we make 3% devices, and with selenization you can make 14%. So everyone sort of lured towards selenization because it feels better to make 14% devices than 3%, but it's not solving the problem.
Yes, it's very interesting that you can see MEG in the sixth film. I'm just wondering, did your group try to measure the nanocrystals in solution to see whether that has MEG? Because for example, for lead selenide, the MR people, they could see MEG in solution as well as in a solar cell. I'm just wondering, does it happen in solution or
Yeah, I should have mentioned that. So the first TAS measurements I showed were on the film, so that's what we looked at initially, and then the 3 different sizes were actually dispersions of nanocrystals. So where we got the MEG threshold, those were dispersions of nanocrystals. So we've done both. And you have to be, so one of the things we checked in the thin films, I don't know how many of you kind of look at carrier multiplication, but you can have, you have charging that can influence your measurements. So some of the early papers on carrier multiplication had really high MEG efficiencies, and the reason was because they weren't accounting for the photocharging that can account. So when you do these measurements, you have to stir the dispersions to eliminate that, and then in the thin films we were translating the stage, okay, so and just making sure that there wasn't a problem with photocharging. But so we've looked at both films and with dispersions.
I got the impression that your nanocrystals were quite macroscopic in size. I'm not sure if you mentioned it or not, but what would be the change in the physics that would allow multiple exciton generation in a nanocrystal that was really fairly large compared to a bulb?
Right. So the copernine selenide nanocrystals we've been looking at are right at that edge you need for quantum confinement. So they're in the TAS measurements I showed of the 3 different sizes, you see the shift in the peak. So you have quantum confinement, but they're relatively large, so to speak. The reason we've been looking at that size range is because that if you go much smaller than that, then the turn-on energy, photon energy for multi-exciton generation ends up going into the UV, like deep in the blue in the UV. So having a a material that has some quantum confinement, but then that your multi-exciton like turn-on wavelength is not so far shifted. So that's really why we've been looking at that size range.
Have you seen a change in the I guess the quantum efficiency as you for multiple generation as you go to smaller sizes?
Yeah, so there we measured the size dependence of that. So the efficiency, well, it's all kind of scaled with the optical gap. So no, we haven't seen any particular. I don't think we've looked at a wide enough size range to really get that. In the size range we're looking at, we actually don't see like. So you see the scaling of the optical gap or the turn-on efficiency with size, but we don't see like an increased efficiency at the same multiplicative of the optical gap for smaller sizes. But we haven't looked at a wide, it's like we haven't gone down to 5 nanometers and smaller diameter and looked there, and partly for experimental reasons because you need like a UV laser to photoexcite in that wavelength range.
So I'm curious about the role of the ligands that you showed. Is it the case you need them in the synthesis to stabilize the particles and keep them from agglomerating?
Right.
But then they also seem to play some sort of crucial role in controlling the behavior, presence or absence of traps and so forth.
Right.
To actually get your final film.
Mm-hmm.
So what are the optimal properties in each case?
Yeah. Yeah, that's right. So they're really important for the synthesis and sort of controlling the size and the dispersibility, so the processing and the deposition. So in the case of lead sulfide nanocrystals, if you look at the work out of NREL and Ted Sargent's group and Moonji Bawendi, they always do ligand exchanges on their nanocrystal film. So what they'll do is they'll deposit the nanocrystals with essentially kind of good capping ligands that enable good dispersibility. And then what they'll do is essentially strip those ligands out with a solution process and do things like exchange with halides, things that are not good capping ligands, but that will passivate electrically the surface. And so so that's been the approach in lead sulfide. And actually by doing that, by either adding a thiol versus like bromide containing surfactant, both the Sargent group and Bawendi's group have measured substantial shifts in electron affinity of these layers. So they'll actually build heterojunctions of lead sulfide nanocrystals with two different types of capping ligands just by doing that. So, so the capping ligands play a role of passivating interfacial traps, for sure, but then they can also play a role of actually shifting the energy levels of the actual nanocrystals. And so when you're making a device, those energy level matching between the different layers is really important. And so I think with the CIGS materials, as a field, we haven't been looking in as much detail as people had for the lead sulfide and lead selenide. And I think partly because a lot of the people making CIGS nanocrystals are all doing selenization. So they're not doing as deposited devices in general. And so in selenization, you don't really care because you're sintering all of the nanocrystals and you're not looking at how do capping ligands influence energy levels. But so that's what we've started looking at. My student who was in Melbourne, I had a student in Melbourne for two months, and he was doing some measurements looking at electron affinity of copper-indium selenide as a function of capping ligand. So I haven't seen the data yet, but he said if you go from a amine to a thiol, the electron affinity can vary by as much as 0.4 volts, which is kind of similar with the lead sulfide. In lead sulfide, they've actually seen electron affinities vary by up to a volt by going from amines to thiols to halides. So I think these capping ligands, and that's somewhat surprising. I think people are learning that that's a role that these ligands can play. For a long time it was, okay, we'll make smaller capping ligands, bring the particles closer together, get more tunneling between particles, and that was kind of the only role. But they actually play a more direct and intimate role in the material properties.
People are knocking on the door already. I think we might have time for one more quick question, if there is one. You both had one already. You had two really quick ones.
Mine's quick. How do you control the size of your nanoparticles, and what size range can you synthesize?
Yeah, so usually mostly by temperature. So higher temperature, larger particles. Also depending, you can add thiols, which will make them much smaller. You can go from 2 nanometers in diameter to 20 nanometers in diameter. Really pretty wide size range.
In silicon, when you get multiple carrier generation, it occurs once you get very strong absorption with direct band-to-band absorption in the silicon. Just from the look of your quantum efficiency, it looked like your absorption must have been getting much stronger in that region anyhow. So are there bands in copper-indium, like it's a strong absorber right at the band edge, the copper-indium diselenide, but are there bands of extra strong absorption at UV energies in that?
Yeah, it's kind of an interesting question. I mean, copper-indium selenide is supposed to be a direct, or people talk about it as a direct band gap semiconductor, but you tend to see kind of a tail in the absorption a lot, and definitely in a lot of the devices we make, where it looks like the absorbance at the band edge is actually fairly weak. And it might be something related to our materials themselves, there. But definitely there is much stronger light absorption in that region. I don't know if it's because of something intrinsic with the electronic structure of copper-indium selenide or just due to the fact that you're more than 3 times the optical gap.
All right, if we could thank Brian once again, and if we could move out of the room fairly quickly, please. To our neighbours.